One spacecraft. 1,400 degrees Celsius. And it should not exist. NASA built a machine that flies closer to the sun than any human object ever has, moving fast enough to cross from New York to Tokyo in under a minute. It cost $1.5 billion. And that's not the strangest part. The strangest part is why it doesn't melt.
692,000 kilometers per hour. Say that number out loud and it means nothing. So picture this instead. New York to Tokyo, a flight that normally takes 14 hours, covered in under 60 seconds. That's the speed NASA needed. Not to escape the sun. To survive getting close to it.
$1.5 billion. That number needs weight. A single deepwater oil rig in the Gulf of Mexico runs about that much to build. A new NFL stadium, the kind with a retractable roof, lands in the same range. NASA spent stadium money, oil rig money, to build something that would fly through fire on purpose. But money wasn't the hard part. Physics was. The surface of the sun glows at roughly 5,500 degrees Celsius. The corona above it, the wispy outer atmosphere the probe was built to fly through, somehow runs hotter, over 1,000,000 degrees. No shield, no metal, nothing built by human hands had ever been asked to survive that close to something that violent. So before launch, there was a meeting inside a NASA conference room. Engineers, contractors, mission planners. Somewhere in that room, a debate that almost killed the project before it left the ground.
This design fails. At this distance, the shield doesn't hold. We're sending $1 billion spacecraft to burn up on live telemetry.
Then show me the math that says otherwise. Because right now, all I have is your confidence.
We don't have it yet. That's the problem.
No one in that room had ever built a shield for these conditions. There was no precedent, no previous mission close enough to steal data from. Whatever came next would have to be invented from scratch, then trusted with $1.5 billion and 9 years of work. They built it anyway. Before we go further, subscribe. It costs you nothing and it decides whether this channel survives. Launched in August 2018, the Parker Solar Probe has now flown closer to the sun than any spacecraft in history, closer than Mercury, closer than anything Icarus ever imagined. And somehow, it keeps sending data back. Not static. Not silence. Full telemetry, orbit after orbit. A shield rated to survive 1,400 degrees Celsius, 30 centimeters from instruments sitting at room temperature. How does that math even work?
That question is exactly what almost stopped the mission. And the engineer who stood up in that room and said it would burn in the first few seconds wasn't being dramatic. He'd run the numbers. What changed his mind is where this story actually starts.
The answer isn't a coating. It isn't a thicker wall. It's carbon foam, sandwiched between two panels of reinforced carbon-carbon composite, the same family of material that protected the nose of the space shuttle during re-entry. Only this time, the target temperature is nearly triple what the shuttle ever faced. Carbon doesn't melt at these temperatures. It sublimates, turning almost directly from solid to gas, at a threshold so high it laughs at 1,400 degrees Celsius. That's the trick nobody advertises on the NASA press page. But heat resistance was never the hard problem. The hard problem was distance. 30 centimeters. That's the gap between a shield glowing white-hot and instruments that need to stay near room temperature to function at all.
30 centimeters is the length of a school ruler. Inside the Johns Hopkins Applied Physics Lab, engineers debated exactly this gap for months before launch. One of them was Betsy Congdon, the lead thermal protection system engineer. Her job wasn't to block heat. It was to make sure almost none of it ever crossed that ruler length of empty space. The shield had to reflect 99% of incoming solar radiation. Not absorb it. Reflect it, like a mirror flinging away a spotlight, because absorbing even 1% of the sun's direct output at that distance would have cooked every circuit behind it. So how do you test a shield for conditions no lab on Earth can fully recreate?
We ran it through the closest thing we had. A solar simulator that could only approximate a fraction of the real flux.
So the first real test was the actual sun.
That's exactly right. And there was no backup plan if the shield failed on approach.
Developing that single shield, the thermal protection system alone, cost engineers years of material testing and roughly $78 million. Not the spacecraft. Not the instruments. Just the 8-foot disk of carbon sitting at the front. $78 million for 8 feet of carbon. That's more than the cost of building most regional airports.
And it worked. The shield held. By 2021, Parker Solar Probe was diving through the corona with its sun-facing side glowing past 1300 degrees Celsius, while the instruments tucked behind it stayed close to 29 degrees. Cool enough to hold in your hand.
So the heat problem was solved. Case closed, mystery over. Except it wasn't.
Because surviving the heat was never the same as surviving what was flying through the heat with it. Somewhere inside that scorching plasma, the spacecraft's instruments started registering something the shield was never designed to stop, and never designed to even detect. Particles behaving in a way no model from the last 60 years had predicted. But the shield only solved half the problem. Because the spacecraft still had to fly straight through something no one had ever measured directly before.
Eugene Parker published his theory in 1958. He said the sun doesn't just emit light. It emits a constant stream of charged particles, a wind, blowing through the entire solar system at hundreds of kilometers per second. Nobody believed him at first. NASA proved him right within 4 years. And for the next 60, his equations became gospel. Billions of dollars in grants. Entire careers. Built on one assumption: the solar wind accelerates smoothly, gradually, the way water speeds up flowing downhill. Clean. Predictable. Provable on a chalkboard.
Parker Solar Probe was supposed to confirm it. Fly close enough, measure the wind directly, close the last gap in a theory older than the engineers who built the spacecraft.
Quick question while we are here, would you have spotted it? Write your answer in the comments. Instead, in 2019, the probe's field's instrument recorded something the 60-year-old model had no name for. The magnetic field wasn't flowing smoothly outward. It was snapping backward, violently, like a whip cracking in reverse, then straightening out again seconds later. Scientists at Johns Hopkins Applied Physics Laboratory called them switchbacks. Thousands of them. Every hour. A switchback is the magnetic field folding on itself in an S-shape, kinking hard enough to fling particles forward like a slingshot. Parker's model never predicted this. It couldn't. In 1958 there was no data close enough to the sun to even see it. So here's the question that mattered more than any dollar figure. If switchbacks were kicking particles forward this hard, this often, was the smooth, gradual acceleration everyone had taught for 6 decades even the main driver at all?
We already told you about the engineer who stood up before launch and said the spacecraft would burn in the first seconds. His name never made the press releases. But his objection was on record inside NASA's own review documents.
His math wasn't wrong about the heat. It was wrong about what the shield was actually made of.
The shield will vaporize on contact with corona density plasma. I've run the thermal models 3 times.
Your models assume absorption. This material doesn't absorb. It rejects 99% before it ever becomes heat.
Then why has no material like this ever survived flight testing at this proximity?
Because nobody has ever been insane enough to fly this close before. That's the whole point of the mission.
He signed off on the mission 3 weeks later. Not because someone changed his mind with a speech. Because the ground testing data on the shield's reflectivity came back, and the numbers matched the theory almost exactly.
The switchbacks are what he never modeled for. Nobody had the equipment to model for them. Not in 1958, not in 2015, not until a spacecraft flew directly into the wind and felt it happen in real time.
60 years of grants. 60 years of textbooks. And one probe, 3 years into its mission, forced researchers to admit the acceleration mechanism was incomplete.
Not wrong. Incomplete. There's a difference, and it's the difference between fixing an equation and rewriting the field.
But the switchbacks weren't the most expensive discovery this mission made. Not even close. Because during the spacecraft's 4th close approach to the sun, something happened to Parker's solar probe itself that had nothing to do with the wind at all.
During that 4th close approach, Parker's solar probe went silent for exactly the amount of time engineers expected. Then it stayed silent 4 minutes longer. 4 minutes, at 450,000 kilometers an hour, headed straight into the corona. Nobody at Johns Hopkins Applied Physics Laboratory could do a single thing about it. Here's the number that should terrify you. Signal delay to the spacecraft during closest approach, 8 minutes, round trip closer to 16. If the autopilot fails, if the shield tilts 1 degree off angle, the ground team finds out only after it's already over.
There is no joystick. There is no abort button that arrives in time.
We asked what that felt like. One APL mission operations engineer described it plainly in a NASA briefing.
You write the sequence months in advance. You test it 100 times on the ground. Then you send it into the corona and you wait, because there's nothing left to do but wait.
If it goes wrong at perihelion, do you even know in time to call it a failure?
No. You know when the spacecraft is supposed to phone home. And then you count the minutes past that number, and you don't say anything out loud.
That's the real design constraint nobody puts in the press release. Not the heat. The distance. Every close approach is a bet placed months earlier, with no way to change your mind once it's rolling. So what happened during those extra 4 minutes? Telemetry showed the spacecraft had autonomously reoriented itself, sensors had briefly lost lock on the sun sensor array, and the onboard computer corrected course without instruction from Earth. It saved itself. Earth found out after the fact.
That's the answer to the question from Chapter 1. The shield never needed a human to save it. It needed a machine built to survive being alone.
If you made it this far, hit subscribe and the bell. The next investigation is already in the works.
By late 2024, Parker's solar probe had completed the closest approach to a star in human history, 6.1 million kilometers from the surface. At that distance, the shield's sun-facing side hit roughly 1,400 degrees Celsius. Instruments 30 centimeters back sat near 29 degrees. Room temperature. Still.
Speed at that pass, roughly 692,000 kilometers an hour. Fast enough to cross the continental United States in under 23 seconds.
Every close approach since has pushed the shield hotter than the last. And every time, the carbon-carbon composite has done exactly what those reflectivity tests predicted back on the ground. No surprises. No melting. Just physics behaving the way one very expensive piece of engineering promised it would.
Which raises an uncomfortable question for the next generation of missions. If this works at 1.4 thousand degrees, how much closer can we actually go? NASA and JPL are already studying successor concepts, some aimed at surviving even nearer approaches, others designed for entirely different stars, using the same reflect-don't-absorb principle this mission proved could survive contact with a star at all.
$1.5 billion. 6 years of construction. A shield that shouldn't work, an autopilot nobody could babysit, and a theory of the sun that stood for 60 years before one spacecraft rewrote part of it. That's the actual price of the data. Not the contract. The risk.
And when the telemetry finally came back after the closest approach in history, engineers looking at the numbers realized something even stranger. They had to redefine what the word close was even supposed to mean.